We began Chapter 10 today, switching gears, to start talking about temperature and thermal equilibrium. And so we had to start thinking about what that means with regard to physics, and how we can use that to talk about the phenomenon that we've already talked about, in some sort of way with regard to energy, and new things. And so we have to define temperature and define how we're using temperature in this course. So, temperature, by one definition, which is called the Zeroth Law of Thermodynamics, basically says that when objects are in a sort of energy or thermal equilibrium with each other, the quantity that is the same between them is called their temperature. So it's one definition of temperature. It's not just how hot or cold something is, it has to do with the relative property of one object compared to another. And when those two things are in a special sort of equilibrium, then that means that their energy states are basically the same in a sort of way, and what is actually the same is their temperature. And so that is defined by the Zeroth Law of Thermodynamics, which says that if object A is in thermal equilibrium with object C, and object B is in thermal equilibrium with object C, then objects A and B are also in thermal equilibrium, and the property that is shared among them is their temperature. So, and the reason why it's called the Zeroth Law, as opposed to the first law, is because it's even more fundamental than the first law. And so it gets that special name of the Zeroth Law because we didn't want to renumber things when physicists were describing what was going on. So we do use the Kelvin scale with regard to our temperatures here. SI units are Celsius and Kelvin, but specifically Kelvin is what we're going to be using, although we'll flip-flop back and forth sometimes with regard to degrees Celsius. The reason we can do that is because the spacing intervals between degrees in Celsius and Kelvin are the same. So it is an easy mapping of one onto the other. However, for Fahrenheit or other temperature scales, you cannot do that because their degree spacing is different. So 1 degree change in Celsius is not equal to 1 degree change in Fahrenheit. There's an extra conversion you have to go in there. But 1 degree change in Celsius is equal to 1 degree change in Kelvin. And so that's why it's useful to use. The reason why we use Kelvin instead of Celsius is because Kelvin actually has no negative temperatures. It begins at 0, at absolute 0, and goes up to infinity. So Celsius then is defined by 0 degrees being the freezing point of water, and 100 degrees being the boiling point of water. And then if you go below 0, you get negative. And it's not nice to actually work with that sort of a scale, because 0 means something, but when you multiply by 0 degrees Celsius, you get 0. So we want to use Kelvin, where the freezing point of water is equal to 273.15 Kelvin, and the boiling point of water is equal to 373.15 Kelvin. Okay. And the absolute 0 of this would be equal to 0 Kelvin. So the lowest temperature you could possibly be at is at 0 Kelvin. So what does 0 Kelvin mean? It means that an object doesn't have any kinetic energy. So another definition of temperature is a measure of the actual speeds of the particles involved in your system. So if you're talking about gas, or a solid, or liquid, then it's the speeds of those particles that make up that object, or make up that collection of things. Okay? And if you keep decreasing the temperature, you decrease their energy. And if you decrease it so much, all the way down to absolute 0, then theoretically, those objects shouldn't be moving. Quantum mechanics still have some other types of energy, but they won't have kinetic energy. At least in this macroscopic sense. And that's why it's also useful to think conceptually as to why we want to talk about Kelvin, because you go from 0 kinetic energy up to an infinite amount of kinetic energy. So, talking about changing temperatures, first of all, an easy conversion between Celsius and Kelvin is simply that you have to add 273.15 to your Celsius degree to get your Kelvin. So, T sub K is equal to T sub degree C plus 273.15. a matter of semantics here, we don't ever say degrees Kelvin when we write down the number, we just say Kelvin. Whereas if you had 1 degree C, you definitely write 1 degrees C. It's just something that is not dumb. We don't put the degree there with the Kelvin. So when you are talking about temperature change with objects, you have to talk about how they will expand or contract based on their properties, based on that physical nature of that object, when they are subjected to a temperature change. And so we need to mention this, and there are 3 different things you can talk about. You can talk about length, you can talk about area, and you can talk about volume. So a change in length when a temperature change is experienced would be equal to alpha times L0 times delta T, where delta L is your change in overall length as a result of this change in temperature delta T over here. L0 is your starting length, and alpha is a coefficient of thermal expansion, length expansion, that depends on the object. It'll be different for everything, for every object out there. If you're talking about area, then delta area is equal to gamma times A0 delta T. So a change in area because of a change in temperature is equal to its initial area times some coefficient, this coefficient being the coefficient of area expansion. For volume, it's the same similar situation. A change in volume because of a change in temperature is related by the initial volume and beta, which is the coefficient of volume expansion. And again, these are all going to be different for different materials. They're going to have units of 1 over degree C or 1 over Kelvin, depending on how you're measuring it. Because we want length on this side, so in order to have length, we need to only have length over here, so these units have to cancel out these units, and so on down the line. Okay. And we can look at this, and we can say, okay, if I have this amount of liquid, and I increase its temperature by 1 degree, then I can figure out what its change in volume has been, and I can then find a new volume. Or I can do the same thing with the area or the length. Or I can decrease the temperature, in which case delta T would be negative, and then we would know that its initial state would be smaller than its final state. Okay, so we can look at this for different objects, for different properties, to know what happens to them when they are subjected to these different temperature changes. And then say, if we're analyzing a problem, we can substitute a different material if it has a different effect on what's going on. And an important thing about this, as I mentioned in class, is the difference between Pyrex and glass. So if you have a glass beaker or a glass coffee pot that is really, really hot, and you put it under very cold water, what happens, it ends up breaking. The reason why it ends up breaking is because of all these stresses that actually end up working their way through the object, since part of it is contracting or expanding and the other part is not. So if you have some vessel like this, as I mentioned in class, and the inside is very hot, and the outside is cold, and you subject it to cold and make it cold, then this outer layer is going to want to contract, and the inner layer is not wanting to contract because it's still hot, it's still happy the way it is. So then you have internal stresses that end up breaking the object apart because the object can't handle it. So Pyrex has a coefficient of length expansion that is 1/3 that of glass. And so when it expands or contracts, it does so at a lower rate, a lower amount than the glass does. And so Pyrex can be used a lot more easily for going from hot to cold environments because it doesn't result in the tremendous amount of stress that the glass experiences. So that's just one example of how we can use this to our advantage. So we're going to be exploring this, and we're going to be exploring other properties of temperature and particles with regard to the ideal gas law in the next lecture.